Hello, this is Sam White again. So, what I wanted to talk about is a little bit on how I contributed, or at least what I've contributed for the design for this current iteration of our robot. And the reason I want to do that is because while you have seen the performance of my robot on the field in competitions, and I've talked a little bit about my role as far as scouting, and a little bit on how I lead the team, both the smaller one and then the bigger one, and then of course you also have access to the PDF of our engineering journal, which has some of my work in it that I've contributed. I don't think I've actually communicated to you yet what exactly I've done for the actual physical engineering part of this. So that's what I'm going to do right now. And as you can see, I got a picture of something up here. What this is this is a picture of the redesigned chassis, right? The chassis where the wheels are supposed to be. Right after I rebuilt it the Friday night before the competition, crunch time, that is. And why did we do that? Well, we found that originally we had a heavy chassis that was really large, and the reason behind that was we wanted to have a lift, okay? And we wanted to have all that structural rigidity from having steel, but because now we're not lifting anymore, we don't necessarily need all that strength and all the weight. That's slowing us down. The other thing is a larger wheelbase means a larger turning radius. And because we're sort of transitioning from, what we had set out to be, which was, a lifting robot that could shoot full court, to a robot that shoots full court but also fields well, right? The field. We want to be able to clean up the field so that at the end of the match, the net looks like this, okay? Not like that net. We want it to look filled. And granted that, this is only filled some of the way. This is a picture of our crunch time, one of our qualification matches. Right, so what we did is we shortened it to what was the minimum length, okay, between this C channel here and this 2x C channel here, right, and that goes up to support the gearing and the intake, okay, for the launcher up here. I'll show you more pictures about that, okay, and then this is the back support, again holding the shape of the launcher ramp. Okay, so what we did, we dropped 2 C channels on each side, okay, and I'll show you pictures of the wheels that we put in and why. One thing to note, cool handles, okay, that prevents us, putting stress on other parts. We don't want to be grabbing the C channels that are up near the lift, right, or I mean the launcher, just because, if we flex that permanently, then, our accuracy is going to change. Maybe it'll start shooting left, right? We don't want that. Okay. So that's sort of the reason behind the smaller chassis, right? And, I took that home and built that because I had the concept idea for that, right? We sort of we have conversations as a group, on what we want, okay, what kind of problems we're dealing with, and the possible solutions, and we hash it out in a discussion. Typically that involves a good bit of graph paper, a good bit of scrap paper, the whiteboard, some markers, a lot of pictures, and that gets translated into the stuff that goes into the journal, the engineering notebook. So what you see here is a robot that happens to be 4300B's robot. And it has Omni wheels in the back, along with high traction normal 4-inch wheels in the front. Okay, both of these are the 4-inch model. And this is considerably slimmer than it used to be. The one thing I'm not going to show you in this, and this you'll have to find in the engineering journal notebook, is the progression from one iteration to the next. Right, I'm going to talk about how I've contributed to the current iteration. And, I'll mention some of the things that are from the past, right? Now, why do we go with two different sets of wheels? Omni wheels work where, you turn it in one direction, okay? It'll drive you in that direction, okay? But if you start to turn, right, and if you think about this as a tank tread, okay, one tread or these two wheels going forward and the other set going the other direction, right, the robot's going to pivot. And if you do, let's say, this one going forward at one speed and this one going forward at a lesser speed, you'll do a turn with an arc to it. Okay. Now, what having these wheels does, these Omni wheels, what that does is that lets it slide to the sides rather than having friction, right? If you wanted to do vectoring, right, you would be able to drive each wheel at independent speeds, and that would let you turn perfectly with high traction wheels. High traction wheels aren't necessarily the best option for this. When if you use Omni wheels, you can get a turn around this point, right? Both of these wheels are going to be high traction. And sorry, this here picture, it's obscured by, a tournament finalist award. Let's see, we can proceed forward. Okay, so you can see we changed it to now have these in the back, the high traction wheels, as opposed to this iteration here. Okay, we changed that. Why? We decided that we didn't want to pivot right here where we were facing, right? This is where the intake is, okay? The intake. We decided that we like the distance of rotating about the back point, pivoting on our back foot, similar to how a basketballer plays, right? So that you get, while you do get an increased radius in the, right here where we're going to be shooting, right? This is increased slightly, which means, slightly more time to turn around, aim at the goal, right, and fill it up. What you benefit from is being able to cover more distance during your turn, right? And that was the happy medium, was changing that. That was based on our experience during crunch time. We wanted to try that out, and that was our reasoning for changing that out. We might actually change these out for Omni wheels before we compete tomorrow, but we're gonna see about that. Okay, so I'm gonna cover more ground other than just the chassis. Let's see. Okay, so I guess I'll touch on this. This wasn't my idea, but we put this back plate in so that we could push piles of balls, and that's useful for when you're a fielding bot. If you have a partner who is shooting the full court, right, you can push some of the local ball piles into the triangle that other teams aren't allowed to cross. Okay, so that's, you can sort of hide some of the balls for late game, and that's useful as far as strategy. So we threw that on there for that purpose, and also to keep them from getting caught in this area, right? We don't want to get tripped up and end up flipping over because we got stuck on a ball. That's stupid mistakes. We try not to make those. Okay. Okay, so this is what I was looking for. So what we have here, this is our intake, okay? We have a two-part intake, right? We have this portion here. Let's see. Yeah, okay, so we have this portion of the intake. And let's imagine that we're from the perspective of a ball. This is going to suck us in, okay, whether we come at it from the side or directly on. Okay. Okay, so these weren't in the right order, my bad. But as the ball gets sucked in, okay, the height of this slides along this shaft, okay, bound by this distance, okay, and that lets us have the correct amount of compression on the ball for the grip without burning out that tread there, right? It has a little bit of leeway so that it can skip, right, a ball right here while picking up another ball here, okay? And this allows us to have 3 in and still pick up one more. So what you will see is right here, this is the high traction tread. And I'm going to skip around again so I can show you a better picture of that. We have high traction tread right in the center. Okay, this is what I want to show you right here, high traction tread, just so that it grabs the ball and pushes it up, right? This is, less traction. It's just a plastic. And it lets the ball slide in because we have these guiders. And these are to keep the ball, going into this 4-inch opening. That was one of the design challenges that we had, was basically raising it up this high and getting it over while still having a good amount of distance of, reach, right? A wide intake to allow us to have, more degrees of freedom as far as which direction we're facing while we're intaking balls. Okay, and to keep balls from getting stuck and pulled up over, I had the idea that maybe we could just use some standoffs right here. So that was the part that I added onto this, along with, helping make this ramp. You might ask, why do we have that ramp there? Well, originally we had things underneath here that we needed to get up and over to. So that's why this ramp is at the shape that it is. Okay, you can see in here there's a secondary set of treads, or the secondary intake. Okay, these get driven right here. And what you might notice, okay, right here, there is two shafts, this one right here and this one, okay, and yet this one doesn't have anything on the other side. Okay, that was because we needed to have the ball pressed between the flat of this secondary intake against this plate. Okay, and that lets it then have a straight tangent when it or a tangent to the flywheel when it touches the flywheel, and then it follows this this arc here. Okay. One thing or at least that I contributed to this part, okay, was guide rails made of 1-bys with limit switches at each end. 2 limit switches so that it centers the ball, and each limit switch, one is a redundancy for the other, programming wise. But what we do is we have a ball, okay, and it comes up until it hits the limit switch. Okay, and then the PID program that Noah works with makes sure that the flywheel is rotating at the right RPM. Okay, Right now we're working with 2,160 RPM for launching. You might notice there's zip ties on this as well as rubber bands. Rubber bands are for traction. Zip ties are to keep this rubber casing of the wheel from separating at high RPM. Okay. Anyway, so that was sort of the programming use of the sensors. We can basically push a button, and it will the program will run all the intakes automatically and automatically shoot all the balls. All you got to do is feed it in there. It's really pretty cool. Then also there's an LCD screen, and I'll show you a picture of that along with the cool functions with that. But back to this, I designed that. Noah had the concept, and we worked it out as a group as far as what he needed to be able to launch the ball, and where he wanted it, right? So he was able to communicate that along with a CAD SketchUp of where he wanted it, and the space that I had to work with, and so I designed this to run on 3 sets of two pinions with an idler pinion between them to run this shaft all from the same motor, right? And this shaft runs it to the other side. We only had one motor to drive this intake. We didn't have room to drive each one at the other end down here because of this gearing. So we ran it with this way, and it doesn't interfere. If this shaft were to continue, it would hit this wheel. Okay. So moving on. Okay, so now we get to actually enter in, and you can see this. Pretty cool. These are some pretty fun pictures to try and capture. Here we are, and we're coming out. Launching. Okay. You might notice cool battery setup, efficiency of space, access to wires. I designed all that cool setup, and then of course we can actually adjust this whole thing. This whole thing is on this standoff. Let's see if I got a. Yeah, you can see it's on these two standoffs and these two standoffs. We can change that height to adjust our center of gravity, which is cool. Here's the that was the LCD. Okay, this is the RPM speed that the ball, or that will. Okay, let me restart that. This is right here is where the RPM speed that we set based on the controller, right? And it starts out at 2160. If we find that it's shooting a little short during a match, you can bump it up or down using the controllers. This is the actual RPM speed. Right now it's not moving, so it's 0. Okay. Battery voltage for the Cortex, useful to know how much it is, so that you can replace it. It's that kind of reminder. This is the up and running time. When I took it, it was only on for 2.7 seconds. Okay, and this is the time between the shots. Okay. So you might notice we have these two motors on an external C channel, and this one on a C channel, and they're all driving these set of gears. That's for a 35-to-1 ratio for the launcher. We started with four motors on the launcher, and we realized we wanted 6 because 4 motors, we were pushing the bounds as far as the power level that we were giving them. When we bumped it up to 6 and used the PID program, which keeps the RPM, the rotational of the flywheel, it keeps it constant. When we combine those two, we're able to feed the motors, a power of, let's say, like 80 on average out of 127, which gives us more room to bump it up. The PID it'll bump the power up to 127 immediately after it fires a ball, and then it'll bring it down and adjust the power based on the speed of this to keep it constant. Excuse me. So what that does is that eliminates the variation in your battery level, making it more dependent on RPM. Okay, and here we get a closer up on the chassis. Pretty slim. We have extra room as far as our bounds, 18 inches cubed. That's the bounds that we're given. Okay. I made this cool attachment right here for this light encoded, or this optical light encoder. There we go. And this is what measures the RPM of the flywheel. Granted, you might notice that it's on a shaft that's not actually the same shaft as the flywheel. That's because right here, this shaft would be going 2,160 RPM. You can't actually have it on this one because it goes too fast for the encoder. And just this past meeting, we were actually having a little bit of trouble with the oscillations of the RPM. That was a huge difficulty. You'll find that on the most recent page in our journal. I actually recorded that one. I fill in sometimes for Vladik for that if he's not there. And so the easy mounting here was easy to change out. We went through tested 3 of these to make sure it wasn't a hardware issue. The rubber bands keep this torsioned correctly so that it doesn't oscillate. Okay, one thing to note, this picture here, this is of the gearing for the launcher, okay, and these pinions, okay, they are for the shaft to go to the secondary intake, right, just to get some orientation for this picture. I took this to show the distance here between these. It's pretty tight. That's what I was designing around, so having Noah draw up CAD diagrams of what this should be was really helpful. Okay, so this I wanted to show you is for to show you how this brings the ball up straight, hits these sensors, okay, and as I move this forward, you'll see that, okay, so you can see that when the ball comes up, it's going to be compressed here, right? That's how we're using the traction on these tread, along with the back wall of this, the ramp, to bring the ball up, right? And then you notice the distance changes a little bit. You don't want too much compression for the flywheel, otherwise, you're applying too much resistance for something that has, high speed, very little torque. Okay. And so this launches it up at a very nice tangent, right? We know that because this is perpendicular to the ground, right? And then this comes out. So it'll be entering this, or the ball and this will come in contact at a pretty even tangent. And then let me pull up the picture of, let's see. Yeah, so the actual arc doesn't extend too high past that. We follow it a little bit. We actually reduced it recently, and that gave us the ability to shoot right up in front of the net, bar shots as we call them, and that's because, well, I guess it's because of the release angle, right? But we did that because we're moving more towards the fielding rather than just full court shots. Okay, so as far as this, I would say that while I've helped design a number of those things on there, I've tried to highlight some of the things that were more original to what I came up with. not to say, I didn't help with any of the other things on here. We work as a team. It's only 4 of us. Noah, Vladik, Alec, and myself. So, we discuss everything as it's occurring, and work as a team to produce the best designs that we can. And then, of course, when we implement it and we find that hey, this doesn't actually work how we want it to, we bring it back and we see what we can improve. The past 2 weeks, we spent a lot of time thinking about doing a new intake, and that's detailed in the engineering notebook. Some of the different ideas we came up with. I was working with Alec on that because after crunch time, we realized that our intake wasn't actually as fast as we wanted it to be, right? And so we started thinking about other ideas of intakes that we've seen or that we think might work. I drew a prototype model of all this space that we had to get through, and where we had to take it for the ramp. But we ended up deciding that because of time constraints, and also that the downsides to any of the options we came up with didn't outweigh the positives as far as making all the changes, that we would just adjust the gearing of this, right? And so this was geared 3-to-1 with a high speed, but we removed the gearing, which reduced friction, and we changed this to a turbo internals. So these pictures reflect the most recent iteration of the robot. Thank you for listening to me ramble a little bit about this, and I hope that you found it somewhat entertaining as well as informative. Thank you very much. Appreciate your time. Have a good one.